Okay, just a really quick example here. We have an open top box with a square base. We know the volume is 108, I guess we can call it units cubed, and we're trying to minimize the surface area. So in this drawing over here, how you want to represent this box is having dimensions x and x along the base because it's a square base, and we can use h for the height. We know the volume equation for this box will be x squared, the area of the base, times the height. But we also know that the volume is 108 units cubed. So we can replace the volume with 108. This is, in fact, the secondary equation, which we will use here in a moment. The primary equation will be the surface area equation. And that's what you get when you multiply to get the areas of each of the walls, which will have a length of a length of x and a height of h. And there are four walls plus the area of the base. So this is what we're trying to minimize. And you'll notice that in this equation, there are two variables. We want there to be one variable. And the reason we want there to be one variable is so that when we take the derivative of this function, we won't have to worry about any implicit differentiation. So here, we can solve this equation for h. And we can see that this equation, when we solve for h, will be 108 over x squared. Once we have this, we can substitute this value in for h in the equation we're trying to minimize, or maximize. In this case, minimize. So we have the surface area equals 432 is what you get when you multiply the 4 times the 108. There will be an x squared in the denominator and an x in the numerator, which would cancel out to be x left over in the denominator plus x squared. Now to find out where it is maximized or minimized, where this surface area is optimized, we have to take the derivative of the surface area. But before we can do that, we have to rewrite this x as an x to the negative 1. Once we do that, we can use the power rule. So over here, the surface area derivative is negative 432 x to the negative 2 power plus 2x. And if I rewrite this so that the x to the negative 2 power here gets bumped back down to the denominator, we have a derivative that looks like this. So what we need to do now is find out where the derivative has critical values. And I think the easiest critical value to see right now is x equals 0, because that's where the derivative is undefined. But we can also set the derivative equal to 0 and solve for x. In order to solve for x, we would have to multiply each term by x squared so we can eliminate this denominator. So we would end up with negative 432 plus 2x cubed equals 0. From there, I can subtract 2x cubed from both sides. I can divide by negative 2. And I can take the cube root of both sides, getting x equals 6. The last thing we need to do is to double check that our critical value from the other side, x equals 6, will give us a minimum. So if we use a number line, and I pick a value, let's see, I put the critical value here on the number line. We know we can't go past 0 because you have to have some actual length to the base. And in fact, we cannot include 0, so this should be a parenthesis. So now we can pick test values. I will pick 1 and 8. And I will evaluate the derivative at these test values. And we're doing this to see if we get an increasing interval to the left of 6, a decreasing interval to the left of 6, and an increasing interval to the right. Because if we get these intervals like this, then there will be a relative minimum at x equals 6. So f prime of 1, when you substitute 1 into this function, you get negative 432 plus 2, which equals negative 430. And it's negative, so the function is decreasing between 0 and 6. Now if we substitute 8 into our function, our derivative, this is the derivative, there we go. And if you substitute the number 8 into this derivative, you'll get that negative 432 divided by 64 simplifies down to, I believe it is 27 over 4, and that would be a negative 27 over 4 plus 16. And that's definitely going to be a positive number. So this interval here to the right of 6 will have derivatives that are positive, which means the original function is increasing, which means there is in fact a relative minimum when x equals 6. So since we knew the original function, the original box had a volume of 108 units cubed, and we know the base would be 6 by 6 because that's the x that we found. This is x. That means we can divide this by 6 to get 18, and we can divide it by 6 again to get 3. This would be the height of the box. So the dimensions would be 6 units wide by 6 units deep by 3 units high.